Today we will talk about simultaneous reactions or sequential reactions. So what are simultaneous reactions? Any two or more chemical reactions occurring at the same time in the system, or in which those kind of reaction in which several sided reactions accompanying the main chemical reaction are taking place in multi steps, or these kind of reactions they are following several paths. They are also known as complex reactions. So in here we have to discuss three main kinds of complex reactions. So the first one is consecutive reaction, the second one is parallel reaction, and the third one is reversible or opposing reactions. Now we are starting from the first kind of complex reaction, that is consecutive reaction, or these are also known as series reactions. So what are consecutive reactions? So those kind of reactions in which the final product is formed through one or more intermediate steps, or the chemical reactions in which the product of one reaction acts as initial reactant for the subsequent reactions. So here we have to give a general example, such as reactant A is converting into product intermediate through rate constant K1, and this intermediate is converting into final product through rate constant K2. So the concentration of uh, reactant and product at different times. So when we have initial time, so the initial concentration of reactant is represented with a naught, and at zero time we have no intermediate, and we don't have any product at the beginning of the reaction. After a certain time t, we have reactant A left A, and the concentration of product B, intermediate form, is B, and similarly this C is C. Typically these kind of reactions can be represented diagrammatically as, on one side this y-axis we have the concentration of reactant and product, and on x-axis we have time of the reaction. So if we have time, zero time, we have reactant or starting material is in the highest concentration, and with the passage of time its concentration is decreasing because it is decomposing into product, and our first product is or intermediate is B. It is formed, its concentration is increasing with the passage of time. Similarly we have at the same time we have the B is decomposing into the final product C, and its concentration is increasing with the passage of time. So at the end we have only the concentration of C, final product is formed. Here this intermediate is formed from reactant B, and this intermediate is then decomposing into final product C, where K1 and K2 are two dependent constants for the first step and second step respectively. If the stoichiometry of this particular reaction is followed, then the initial concentration of reactant B, that is at any time, is given by the concentration of A at any time, and sum of A is decomposed into intermediate B and sum into final product C at any time. Now we have to calculate the differential rate for different steps. So the rate of disappearance of A is directly proportional to the concentration of A with the rate constant K1, and negative sign show the decrease in concentration. For the intermediate B, the rate of change of its concentration is actually the sum of two rate constants, R1 and R2, and I would like to explain it here because intermediate B is formed in the first step, and at the same time it is consumed in the second step. So its concentration is increasing in the first step and it's decreasing in the second step. So this will be the sum of two rate. In the first step it is formed, so its rate is given by proportional to the concentration of A, and with the positive sign because its concentration is increasing. In the next step it is consumed, so its rate is proportional to the concentration of B, with negative sign show the decrease in the concentration. Just putting the value of R1 and R2 in equation 3, so we are getting the overall rate of change of concentration with respect to time. this intermediate. Similarly, for the final product C, the rate of formation is actually equal to the rate of disappearance of B, but with a positive sign, and this opposite sign, that is positive sign. This shows that the concentration of C is increasing with the passage of time, and that is formed from intermediate B. Now we are solving all these equations. So equation 2 is represent a first order differential equation. This can be solved by integrating this equation between limit. If we have time 0, we have the reactant concentration represented with a naught. After time t, any time t, the reactant concentration is represented with the a. So just integrating this equation between initial limit and final limit, this initial time, final time, and applying this general formula for integration. If we have 1 over x dx integrating, we are getting ln x, but this independent integration, we don't have limits. So we are actually putting integration constant plus c here. This is between limit, applying the limit. So this is the same negative sign. After a while, we have to transfer the negative sign here. So log final limit minus log initial limit, and log after applying the negative sign. Just we have this equation. This is the same equation. After rearranging, we have to solve this log term by taking exponential. So taking exponential, we are getting this. So from this we can calculate. This equation is solved for the concentration of A and rate constant for the first step. So this equation 6. Putting this value of equation 6 in equation 4. This equation 4, we put the concentration of A at any time. So we are getting, now we have actually to solve for the concentration of B intermediate. So this is the differential equation, but after just putting the value, we will solve this. After rearranging this equation, we got equation 7, and this equation 7 is actually a linear differential equation with constant coefficient, this k2, k1, and a simple linear differential equation is dy over dx plus y minus x is equal to 0. So this is variable y, x. So we have this general equation y minus x, or another one, a little complicated one, dy over dx plus 4x xy plus ln x is equal to 0. So these are different general linear differential equations. So for these kind of linear differential equation, we are supposing a solution, that is b. We are putting the value of b is equal to e raised minus k2t, differentiating equation x with respect to t. So differentiating this can be considered, this one a is a and this is b. So differentiating a and keeping b constant, and in the other case we plus differentiating a and keeping b constant. So this applying the common differential formula, applying this general differentiation rule to the exponential factor. So differentiating e raised kx with respect to x, so we are getting e raised kx. Similarly, we already applied here. So to the exponential factor, similar to du over dt. So db over dt is equal to minus k to u e raised minus k to t plus e raised minus k to t du over dt. Putting the value of this b and this differential factor in equation 7. So after putting the value, just cancelling the same factor on both sides. So we are getting, after rearranging, we are getting the final equation 8. So this equation 8 can be solved because this is a differential equation, can be solved on integration of this equation. So just transferring this dt to another side, and after applying this common integral formula e raised x dx, so we are getting e raised x, and if we have e raised xt dx, so we are getting 1 over t e raised xt. So this is the general mathematical formula for integrating the exponential factor. we applied the same formula over here. So we after solving this, applying this formula here, so after solving this we got 1 over k2 minus k1 e raised minus, so this minus sign we just took common already, t plus c is constant. Solving this equation we can solve by integrating this equation. For integration we have to use this general integration formula. If you have e raised x on integration we are getting e raised x, and if you have e raised xt dx, so on integration we are getting 1 over t e raised xt. So on integration of this equation, this is the constant term we have to take out of integral sign, and on integrating this one we are getting this solution 1 over k2 minus k1 e raised minus k1 t. Putting the value of u in equation b, so just putting the value of u over here, and this is we have to take outside from the value, and after solving this, multiplying with this exponential factor, so we got this value. And for finding the value of c, because we have, this is a constant integration, we have to find its value and put the value of this c over here. So we are just supposing that at time t is equal to 0, the concentration of b is equal to initial concentration, putting this here. So after putting this value in this equation, this b is equal to b naught and t is equal to 0. So we are getting actually exponential factor, this will be 1 and this will be is equal to 1. So we are getting the value of c here, and putting this value of c here in this equation, so we got the concentration of b in this equation 9. So this is the expression for the concentration of intermediate b in terms of two rate constant k1 and k2. The concentration of b in equation 9 is given here, and this has two parts. The first part represents the disappearance of a, so this is the show the disappearance of a, and in the b, this show the appearance, or this is the reaction or consumption of b, because b is formed and at the same time b is consumed. So putting the value b naught is equal to 0 in equation 9, it becomes like, it is more simplified, so this become like this term becomes 0 and we have only the first term is remaining. And putting the value of a and b value in equation, our basic equation, so just putting the value of a and b in this equation, so we can get the concentration of this c, the final, which is the final product. Our final product concentration can be obtained by putting the value of a and b, and this a naught is the initial concentration. So this is our overall equation, series or multi-step reaction. So we can get the concentration of c by putting the value of this a and this b, taking a naught common. So after taking a naught common, so we have this 11 equation 11, this is our final equation. This equation can be simplified a little more. This is the form of for the final product c. So we are assuming that if the intermediate is more reactive than the starting material, so k2 is more than k1, so this k1, this picture can be ignored and we have this equation simplified. This is for the final product, the concentration of final product in terms of two rate constant. Example is decomposition of dimethyl ether. So dimethyl ether can be decomposed in first step to methane and formaldehyde. In the second step it can be decomposed into hydrogen and carbon monoxide. The next example is decomposition of ethylene oxide. Ethynyl oxide in the first step can be decomposed into acetaldehyde, and in the next step it can be decomposed into methane plus carbon monoxide. Similarly, the radioactive decay of nuclide, that is radioactive nucleus, into another radioactive nucleus, and that radioactive nucleus can be decayed into another one, and this process is continued and taking place in several steps. So this is also an example of series reactions or multi-step reactions or consecutive reactions.